In this video, we are going to discuss about the part 4 of the chemical equilibrium. In the last sessions, we discussed about in detail about the chemical equilibrium constant, applications, characteristics, and all. And here we are continuing with the equilibrium constant, where we need to calculate the equilibrium constants like Kc and Kp by knowing the number of moles of the reactants that are consumed during the equilibrium and all. And after that, we are going to check the Lechatlier principle also, which is very useful topic in both JEE mains and NEET exams. Let's strengthen our basics now. Suppose if we consider the PCl5 gives rise to PCl3 plus Cl2, let A are the number of moles that we have taken initially in the vessel. As we take only the reactants, products moles are 0, 0, 0, 0. And let us suppose that after consumption of some X moles from PCl5, equilibrium is established. Then what are the number of moles that are at equilibrium? A minus X. As X moles are consumed, X moles of PCl3 and Cl2 are formed. Hence, the number of moles of PCl3 and Cl2 are X comma X. And in order to write the Kc expression, we need the active masses, or you can say the concentrations. So A minus X by V, that is nothing but N by V is the formula for calculating the concentrations, and hence the concentrations are A minus X by V, X by V, and X by V. Let's substitute all these terms in the Kc. Then the final expression for the Kc value is X by V into X by V divided by A minus X by V. This is the expression for Kc. Then how to calculate the expression for Kp? We know already it is the equilibrium constant in terms of partial pressures. So partial pressure of PCl3 into partial pressure of Cl2 divided by partial pressure of PCl5. Always partial pressure we get by multiplying the mole fraction in with that of the total pressure or equilibrium pressure. How to calculate the mole fraction? Mole fraction nothing but, for example, if we consider mole fraction of PCl3, NPCl3, number of moles of PCl3 divided by total moles we have to write. Then, how to calculate the total number of moles? Check this one, A minus X, X, and then X. If we sum these three terms, you will get A plus X as the total number of moles. So, if we consider PPCl3, number of moles of PCl3, X divided by A plus X into capital P will be the partial pressure of PCl3. If we do the same thing for the remaining terms, we will get the Kp expression as X by A plus X into P, X by A plus X into P divided by A minus X by A plus X into P. Later you can simplify this one. Let's simplify here now. X square by A plus X whole square into P square into the denominator fraction reverse we have to take now. So A plus X by A minus X into P. That P will be where it is? It is at the denominator itself. So I'm writing the P here. So by cancelling the like terms here, you will get X square by A square minus X square into P as A plus B into A minus B is equal to A square minus B square formula. And this is the final expression for the Kp for the given equation. And we know already how to write the relation between Kp and Kc just by knowing the delta N value. Delta N value for PCl3 gives rise to, sorry, PCl5 gives rise to PCl3 plus Cl2 nothing but 2 minus 1, and hence we have written the 1 here. So this is how to express the Kp and Kc by knowing the terms like the number of moles at equilibrium or concentrations at equilibrium. Now, let's move to the next example. Suppose if we consider N2O4 gives rise to 2NO2, let us suppose that A is the number of moles of N2O4 that we have taken in the vessel, and as initially we don't take that's 0 or the number of moles of NO2. Now listen carefully. Here we are going to introduce the new term that is called degree of dissociation. What is meant by degree of dissociation? Suppose, suppose if I consider only 1 mole of N2O4, how many moles from 1 mole dissociated into products? The number of moles that are dissociated for 1 mole of the reactant is nothing but alpha. So for 1 mole, how many moles dissociated? Nothing but degree of dissociation. Initially, how many moles we have taken? A moles we have taken. If 1 mole alpha moles are dissociated, for A moles, A alpha moles will be dissociated. And hence the remaining moles we have written as A minus A alpha. When A alpha moles of N2O4 conjunes, then definitely 2A alpha will be produced. It is according to the equation. According to the equation, 1 mole of N2O4 definitely gives 2 moles of NO2. So A alpha moles readily gives 2A alpha moles of NO2. Then concentration means always number of moles by volume. So A minus A alpha by volume, 2A alpha by volume. And here alpha is nothing but the degree of dissociation where we get the fraction of total number of molecules under dissociation, which is nothing but the fraction of total moles that are undergoing dissociation. Understand? Now, suppose again for this equation, if we want to know the total number of moles in order to calculate the Kp, A minus A alpha plus 2A alpha. In that case, A plus A alpha we get as the total number of moles. Let's first write the Kc expression. So Kc expression will be the 2A alpha by V whole square divided by A minus A alpha by V. This also we can simplify. How to simplify? 4A square alpha square divided by A into 1 minus alpha by V. So let's by V here also. Let's take the reverse of the denominator fraction so that you will get V divided by A into 1 minus alpha. V and V gets cancelled. A and A gets cancelled. So that 4A alpha square divided by 1 minus alpha is the final expression for Kc in terms of degree of dissociation alpha. Similarly, you can calculate even the Kp also. That's how to calculate the Kp and the Kc. Now, let's get into the Lechatlier principle, which is very interesting and important topic. If a change is applied to the system at equilibrium, that means if the system is at already equilibrium, and if we try to change something, or if we try to apply the change for the equilibrium, then what equilibrium will do? It will be shifted in that direction in which it can minimize the effect of the change applied. And equilibrium is established again under the new conditions. That means, suppose if we consider the system which is already at equilibrium, if we apply any change, like change the temperature, change in the pressure or volume, or if we increase the concentration or decrease the concentration, Then, then, then what equilibrium will do? It shifts in the opposite direction to nullify the applied change. That means if we do, if we increase the temperature, then the equilibrium will shift in the decreasing temperature direction. If we increase the pressure, equilibrium itself will shift in which direction the pressure decreases to nullify the effect so that it gets the equilibrium back. Once again, if we increase or decrease either of these factors, definitely equilibrium will be disturbed. The system always spontaneously want to get back that equilibrium. Then what it will do? It will shift in a direction opposite to that of our change, our what we have applied the change, so that the equilibrium re-establishes again is all about the core point of Lechatlier principle. Let's consider the example N2 plus 3H2 gives rise to 2NH3, and the first factor is about the concentration. Before applying any change, let us see what will happen in the reaction. What is happening in the reaction without considering any changes. If we consider the forward reaction, reactants are converting into the products. That means in this direction, in the forward direction, the reactants concentrations are decreasing and products concentrations are increasing. If we consider the backward reaction, in the backward reaction, the products are converting into reactants. That means reactants concentrations are increasing and products concentrations are decreasing. This is what exactly happening regarding the concentration terms. The first factor is the concentration. Now we are going to apply the change. That means we are going to either decrease or increase either the products or the reactants. For example, if the concentrations of reactants are increased that we are applying, so what equilibrium will do? Exactly opposite. That means reactants concentrations must decrease so that equilibrium will be established, and equilibrium uh, will be established in the decreasing direction, decreasing concentration of directions of the reactants. So where the reactants are decreasing here in this case, that means in the forward direction, the reactants concentrations are decreasing. Hence, you can see here the reaction shift in the forward direction. That is the main thing of Lechatlier principle. When once if you know one term or at least one factor exactly what is what will happen, then automatically all the things are very simple and interesting. And here as the reactants concentrations are increased, forward reaction takes place. Similarly, if products are increased, exactly opposite we have taken, and hence instead of forward direction, backward reaction favors for some time and again until the equilibrium re-establishes. Okay. And here what is the note? The addition of any solid component does not affect the equilibrium. Solid component, if we consider as the concentration is constant for solids, we taken as unity, right? So there is no effect on addition of any solid component. Let's move to the effect of volume now. If volume is increased, if volume is increased, no doubt automatically pressure decreases. Then Suppose if we consider reaction, before going to the term pressure and what is happening to the pressure in any reaction, let us see let us take the reaction A of gas plus B of gas gives rise to C of gas. In this reaction, the number of gaseous moles are more on the left hand side and less on the right hand side. That means pressure is less on the right hand side and more on the left hand side. So, suppose if I take the forward reaction, more pressure is converting into the less pressure. That means that means the pressure is decreasing. In the backward direction, less pressure is converting into the more pressure. That means pressure is increasing. So, in this particular example, in the forward reaction, the pressure is decreasing. In the backward reaction, the pressure is increasing. According to the Lechatlier principle, suppose if we increase, if we uh, decrease the pressure, a minute, before going to check that also, we need to check for the delta N here. Delta N is how much here? Delta N, if we consider products minus reactants, that is nothing but 1 minus 2, that is nothing but minus 1 less than 0. So, when delta N is less than 0, forward reaction pressure is decreasing, backward reaction pressure is increasing. That is exactly all about the given equation. We did not do anything. Just by looking at the equation, we analyzed all the things that are connected with the equation. Now we are going to bring a change. What is that change? Suppose if we increase the volume, pressure automatically decreases. As we are decreasing the pressure, in the increasing pressure direction, equilibrium shifts. In which direction the pressure is increasing? Backward direction for delta N less than 0. So the conclusion here is, if volume is increased, if delta Mg is less than 0, then the reaction shift in the backward direction. That is what we got here. Understand? So if this one thing, if you understand, the remaining terms you can automatically guess, right? So instead of delta n less than 0, if I take delta n greater than 0, again if we decrease the pressure, automatically the opposite of it, that means forward reaction takes place to the greater extent in order to attain the equilibrium. Right? Now, suppose if we consider H2 of gas plus I2 of gas gives rise to 2HI of gas, 2HI of gas, where the number of moles are same on both reactants and product side, in which the delta N is 0. As the same number of moles are on both the sides, there is no pressure change on both the sides. Hence, the volume or the pressure has no effect on this type of equilibrium. That means whenever delta N is 0, reaction will not shift. There is no effect of either the volume or the pressure on the equilibrium. Understand or not? And if you once know the effect of volume, you will come to know even the effect of pressure, because we came to know the pressure and we know already about the pressure and the volume, which are inversely proportional to each other. And we already discussed what happens when pressure decreases, what happens when pressure increases, how to check for either the volume term and the pressure term. We need to take the delta n value, depending upon the delta n value only, delta n value only, we can check the pressure effect. Here, if delta ng is equal to 0, it is not the number of effect, it is no effect, right? If delta n is equal to 0, for pressure or volume, no effect on the equilibrium, right? Now listen carefully. As we know already, suppose if we consider delta n less than 0, delta n less than 0, and if P is decreased, the pressure is decreased, no doubt the backward reaction takes place. That is what we discussed even in the case of effect of volume. So it is the similar case, and if we increase the pressure, no doubt the forward reaction shift for delta n less than 0. For delta n greater than 0, exactly opposite case. That is what we have written here. Delta n greater than 0 for this type of reactions, and the backward reaction takes place if we increase the pressure, and the forward reaction takes place if we decrease the pressure. That is all about the pressure and volume effects on the equilibrium. Let us discuss the effect of temperature on equilibrium. In order to check the effect of temperature, we need to check the reaction is whether the exothermic reaction or endothermic reaction, especially the forward reaction. For example, if the forward reaction is exothermic, that means A plus B gives C. If it is an exothermic reaction, heat is produced as a product in the forward direction. And automatically the backward reaction will be endothermic. Automatically the backward reaction will be endothermic, right? Anyhow, let us see on which side the temperature is more. Heat is on the right side. That means on the right hand side the temperature is more. Automatically on the left hand side the temperature will be less, right? Technically, theoretically, right? Now, suppose if we consider the forward direction, less temperature is converting into the more temperature means temperature is increasing. And in the backward reaction, if we consider, more temperature is converting into the less temperature means the temperature is decreasing. We did not do anything for the given equation, but we have just analyzed what is happening for the temperature in the forward and backward direction. Now, suppose if we apply the change, now let us go to the changes now. Suppose for this reaction, if we increase the temperature, then automatically equilibrium itself, what in which direction it proceeds? In the direction of decreasing of temperature to nullify our change. Now, if we increase the temperature decreasing direction equilibrium shifts. Temperature is decreasing in the backward reaction. That means after applying this change, the backward reaction takes place to the greater extent, and you can say that equilibrium shift in backward direction. Understand or not? And the opposite case you can take for the same equation. Suppose if we decrease the temperature, decrease the temperature, automatically the forward reaction takes place to the greater extent to achieve the equilibrium for exothermic. Then for endothermic, exactly opposite case. By increasing the temperature, forward reaction. By decreasing the temperature, backward reaction for endothermic reaction. This is how to check the effect of temperature, pressure, concentration, and volume according to the Lechatlier principle. Because according to the Lechatlier principle, if we apply any change, the equilibrium on its own will shift towards the backward direction or forward direction in order to nullify that change. That is exactly opposite process of what we have done to the equilibrium. Is all about the Lechatier's principle. And here one thing is there regarding the temperature. Temperature dependence we can also express in terms of Van Hoff factor. That is nothing but log K2 by K1 is equal to delta H divided by 2.303 into R into T2 minus T1 by T1 T2. Here K2 and K1 are the equilibrium constants at T2 and T1. That means if we change the temperatures either from T2 to T1 or T1 to T2, then what happens to the K values, equilibrium constant values? Because we know equilibrium constant only depends upon the temperature. The equilibrium constant value changes with the temperature, and hence we are going to check even the equilibrium constant changes when the temperature changes. Okay, we came to know that, for example, if delta H is positive, that is endothermic reaction. That is endothermic reaction. If delta H is negative, that is nothing but exothermic reaction. T2 greater than T1 means what happens? T2 greater than T1 means we increased the temperature. For exothermic reaction, if we increase the temperature, for exothermic reaction, if we increase the temperature, we already know the backward reaction favors. If the backward reaction favors, definitely the K2 value will be less when compared with K1. That is what they have written here. And exactly the opposite case for endothermic. Understand? Here the equilibrium constant depends on temperature because the rate constant depends on the temperature according to the Arrhenius equation. According to the Arrhenius equation. And whenever we add some inert gas to the equilibrium, at constant volume, though we add the inert gas, there is no change or effect at constant volume on the equilibrium. But at constant pressure, if we add inert gas to the equilibrium, that means we added the gas under the constant pressure, means pressure here as we add inert gas, volume increases, pressure decreases. To maintain the same pressure, the equilibrium will shift in the direction where the pressure increases. Where the pressure increases, on which side the number of gases moles increase are more, then that side the pressure increases. So equilibrium will shift in the direction in which the larger number of moles of gases are formed. So you can take any example and the conclusions here are if delta N is less than 0, if we add inert gas, as the volume is increasing, pressure is decreasing, as we discussed already, the backward reaction is favorable. And exactly opposite case is this one. And we know already delta N is equal to 0 means there is no effect of pressure on the equilibrium. So the conclusions you can note down here, right? This is all about the Lee-Chartier's principle. Short, crystal, and clear, right? Thanks for watching the video. If you really like the video, give thumbs up for the video. Thank you.